Welcome, everybody. I'm sure we'll all agree on one thing, and that's knowledge is empowering. Today, I wanted to take you on a sweet journey, one of sugars and the way sugars play such an essential role in human biology. They're essential in every aspect of life. I'm sure there are very few people that would know sugars are in space, out of space. The building blocks exist in a wonderful prebiotic layer in outer space, and these are essential parts that have landed, of course, on Earth to build sugars that we use in our biology. I want you to think about these donuts as cells. And what you see on these donuts is the sugar coating. And that sugar coating reflects exactly what happens in every cell in our body. Every cell in our body has this wonderful sugar decoration associated with it. And that's where the interplay in human biology comes in. A little bit more technical. Here now we have a more structural view of a cell, a single cell. And what you see on that single cell are these wonderful little blue dots extending out from what I term the membrane. Those little blue dots all joined together are in fact that sugar coating that you saw on the donuts. And those are the sugars that engage in communication with other cells, communication with other biomolecules that we need on a daily basis to survive. And unfortunately for us, as you can see there, also with microbes such as viruses and parasites and bacteria. So these pathogens actually engage that sugar coat to commence disease and propagate disease through the human body. That's what we're interested in. We understand a part of that pathway, and you could imagine that if we can actually stop that engagement, and what you can see here is on this virus, and I'm focusing on viruses today, that this arm of the virus locks on to that particular carbohydrate, that little blue dot, in a very specific manner. And that little end to the virus has a shape, an architecture, like a door, if you will, a cavity. And so, of course, everybody in the room would already agree that, well, if you can actually block that door, lock it open, you'll stop that engagement of that virus causing further infection. And that's exactly what we're trying to do. Better understand that process to actually give then drugs. I said that I'd focus on viruses, and why is that? Viruses are in fact the silent terrorists of the 21st century. Unfortunately, we are not armed to combat significant viral diseases, and you can see the numbers there are very, very significant. We know there's a major pandemic with HIV, for example. Hepatitis virus also causes significant infection, as you can see in terms of the numbers. We've had scares in terms of viruses that have appeared out of the blue, SARS virus, for example, that caused major economic impact in the world. We were not prepared at all for that particular virus. And other viruses that I've mentioned there, rotavirus, influenza virus, and very recently, of course, the re-emergence of Ebola virus. All horrifying consequences that we are not prepared for. Flu virus remains a problem, though we have some very comprehensive drugs. Viruses have the capacity to change the way that they present themselves, and unfortunately, drug resistance is also an issue. So a lot of work needs to continue. Flu virus is one of those perfect examples of how a virus engages sugars, on this occasion in our upper respiratory tract. This virus hunts for specific sugars attached to our cells in our upper respiratory tract to stick to like a glue. And that causes that first part of infection. And then it uses further carbohydrates to propagate infection. Hollywood has its own description, of course, of major pathogen outbreaks. We know the movies Outbreak, we know the movies Contagion, for example. Interestingly enough, there is scientific accuracy, some scientific accuracy in those movies. And I'm sure for those who have seen those sorts of movies, you see images like this, where, of course, the scientist is actually dressed up, completely covered in clobber that prevents any infection of that particular individual. By the way, that's a real image. That's in Africa, in the Ebola outbreak. So there is consistency in some ways between Hollywood and what we are actually looking at today. Unfortunately for us, there are a lot of mammalian vectors, hosts, that can harbour these viruses. For example, Ebola virus, and indeed another virus that has raised its ugly head in this country, Hendra virus. Flying foxes live quite happily with these viruses, which is very intriguing when you think about it. Why? Why do they not suffer the significant loss of life that, unfortunately, when these viruses get into humans, actually cause? And that's a big study that's going on right now to better understand that. The bottom line is we need drugs to obviously cure the diseases caused by these viruses when they actually get into man. And that's a part of our job in terms of drug discovery. Fortunately, Hendra virus has been tackled, at least in our equine industry. Vaccines have been developed now that appear to be adequate in protecting, of course, horses, not humans. We're not that far yet. So right now, if we had a major outbreak of a Hendra virus that became a truly pandemic virus, we're not protected. We are completely at its pleasure. And unfortunately, we know when that virus gets into man, around 50% die. That's a big statement. And that's just one virus. There are many emerging viruses that we still have no treatments for. So, I've talked about sugars, how many viruses actually use carbohydrates to engage as first point of contact, like an alien coming down from outer space. That alien wants to land in the right spot to make communication with the right person. The virus does exactly the same thing. So what we're trying to do is to crack that code. We want to know what is that signature pattern, what is that unique space where that virus wants to latch onto to cause infection. If we can block that process by blocking that architecture, locking that door open, we'll have a new drug. So here now is a virus attacking a cell, and you can see here, this one is in free space at the moment, moving in. Here is a virus actually already attached. It's picked where it wants to land, and it's very, very specific. So a flu virus, of course, won't just come and land anywhere in your body. It actually lands at a specific cell for a very specific reason, such that it can cause significant infection. So the more we can understand about that contact point, the more we can develop new drugs. Drug discovery is a multidisciplinary science. It's not just chemistry. It's not biology alone. It's not physics. It's not computational science alone. It's all of those working together. And that's modern science. That's modern science, particularly in drug discovery. All of these disciplines work together to understand not just the process, but also to come up with a cure. And that's what we're about. What we want to do is to lock that door open. And what you see here is a molecule now in that architecture of the virus that allows it to latch onto sugars. Blocking that cavity with a molecule, with a chemically synthesized molecule, will stop that virus from propagating infection. A new drug, perhaps. A new cure for Ebola, perhaps. Wonderful opportunity. Of course, at the end of the day, we need to get those drugs into our pharmacies to treat these significant diseases, to prevent significant loss of life. I hope that what I've done for you today is convince you that sugars are important. They are attached to every cell. It is no wonder that many of these organisms utilize them to cause and propagate infection. Knowledge is empowering. The more we understand about those processes, the more opportunity we have to create new drugs based on that knowledge. That's what we're about. Thank you.